We're going to start with looking at a linear transformation from V to W, where V and W are both R2. And we're going to have the following transformation. T of xy equals 2x minus y, and 3y minus 2x. And here, x and y are vectors. That is the tuple xy. So xy is a real number, then a real number. And we're going to compute the matrix given the two bases, alpha being the vectors 1, 0, or 1, 1, 1, 2, and beta being the vectors standard first basis and the standard second basis vector. And then we're given a third vector v being 1, 3. And we're going to be doing 4 questions. And the first question we're going to do is compute the alpha beta matrix representation of T. So to do this, what we need to do is we need to look at what T of 1, 1 is, because I'm going to be looking at T in terms of my alpha basis, and I'm going to be going one at a time. We're looking at what T of 1 does into this formula here. So 1, 1, this means that it's going to be 2 times 1 minus 1. 3 times 1 minus 2 times 1, which is equal to 1, 1. Okay. But now I need to represent 1, 1 using the standard basis. So this is going to equal 1, 0 plus 0, 1, which equals 1e1 plus 1e2. Now for the second equation, I'm looking at T of 1, 2. This is going to be 2 times 1 minus 2. 3 times 2 minus 2 times 1, which equals 0, 4, which is going to be 0, 1 by 0, 0 plus 4, 0, 1, or 0e1 plus 4e2. Now, taking this information here, I can get that T of alpha beta is equal to, and now I take the coefficients here to make my first column. So they make my first column 1, 1. And then these coefficients form my second column 0, 4. And there's my matrix representation. I'm then asked to compute the coordinates vector for V in the basis alpha. So V, we have 1, 3. So I'm looking at 1, 3, and I want to represent it equaling some A 1, 1 plus B 1, 2, which implies that A plus B, A plus 2B is equal to 1, 3, which gives the system of equations A plus B equals 1, A plus 2B equals 3. So a solution to the system of equations gives me my linear combination of my two vectors. So now I'm going to make my augmented matrix 1, 1, 1, 2 equal to 1, 3. And doing row 2 minus row 1, replacing row 2, will give 1, 1, 1, 0, 1, 2. And now row 1 minus row 2, replacing row 1 will give 1, 0, minus 1, 0, 1, 2, which gives the following equivalent system equations. A equals -1 and B equals 2. So this means that my V represented using alpha is equal to the vector -1, 2. Remember, the order matters. The order of alpha is 1, 1, 1 minus 2. That's why it was A, it came first, then B. That's why it's the coefficient that comes first. That gets multiplied by the first vector in alpha. That's multiplied by the second vector. Now we're asked to compute T of V. So we're going to look at what does T do to the vector 1, 3. If we scroll up just a little bit to recall what that is, we get 2 times 1 minus 3, 3 times 3 minus 2 times 1, which equals -1, 7. Now, we're now going to verify that the matrix representation of T, this should be the matrix representation of T in the alpha beta basis times the coordinates vector of V in alpha equals the coordinates vector of TV in beta. And to do this, we need to do two things. First, we need to compute what TV in beta is equal to. We also need to look at what is the matrix representation of T with alpha beta times the coordinates vector of V in alpha is equal to. First, I'm going to look at this top. Well, we have -1, 7. So we're looking at the coordinates vector of -1, 7 in beta. And before we give this answer, we're just going to go off to the side here. I'm going to do a different color to look at off the side work. We're going to look at what -1, 7 equals A times 1, 0 plus B times 0, 1. And because it's the standard basis, we can break it apart. And we can see that A equals -1 and B equals 7. And if you created your homogeneous or your system of equations and solved, you would see that the only solution is A equaling -1 and B equaling 7. And you were already in reduced echelon form. So this means that this vector, the coordinates of this vector are -1, 7. Okay, and we want to show that the matrix multiplication also gives us -1, 7. So let's take what our matrix representation of T is, which was 1, 1, 0, 4. So we're going to take 1, 1, 0, 4. And we're going to multiply this by our coordinates vector -1, 2. And remember, when we're multiplying, we get 1 times -1 plus 0 times 2. 0 times 2. Now the next row we get 1 times -1 plus 4 times 2. And we can see that we do in fact get -1. Now for this first video, it was a relatively straightforward. I encourage you, if you didn't follow along, to try it again a few times. In the next videos, what we're going to do is we're going to increase the complexity slowly. So instead of having our output basis be the standard basis, what we can do is we can have our output basis being alpha instead, or a non-standard basis. This will increase complexity. And through the week, we're gonna do things like use polynomials instead of vectors in Rn. We're gonna be going from one dimension to another dimension. Those type of ideas, just to increase the complexity of it.